Okay, so good day everyone. Our topic for today is about foundation of business intelligence, databases, and information management. So after after this lesson, you will be able to answer the following questions. So what are the problem of managing data resources in a traditional file? Environment and how are they solved by a database management system? What are the major capabilities of database management system? And why is a relational DBMS so powerful? What are some important principles of database design? What are the principal tools and technologies for accessing information from databases to improve business performance and decision making? And why are information policy, data administration, and data quality assurance essential for managing the firm's data resources? Okay, an effective information system provides users with accurate, timely, and relevant information. Accurate information is free of errors. Information is timely when it is available to decision makers when it is needed. Information is relevant when it is useful and appropriate for the types of work and decision that require it. You might be surprised to learn that many businesses don't have timely, accurate, or relevant information because the data in their information system have been poorly organized and maintained. That's why data management is so essential. So to understand the problem, let's look at how information system arrange data in computer files and traditional methods of file management. Database technology cuts through many of the problems of traditional file organization. A more rigorous definition of a database is a collection of data organized to serve many applications efficiently by centralizing the data and controlling redundant data rather than storing data in separate files for each application. Data is stored so as to appear to users as being stored in only one location. A single database services multiple applications. For example, instead of a corporation storing employee data in separate information systems and separate files for personnel, payroll, and benefits, the corporation should create a single common human resources databases. Business use their databases to keep track of basic transactions such as paying suppliers, processing orders, keeping track of customers, and paying employees. But they are also need databases to provide information that help the company run the business more efficiently and help managers and employees make better decisions. If company wants to know which product is the most popular or who is its most profitable customer, the answer lies on the data. For example, by analyzing data from customer credit card purchases, for example, in SM, by analyzing data, for example, in SM restaurant chain, learned that quality was more important than price for most of its customer who were college educated and like fine wine. Acting on these informations, the chain introduced vegetarian dishes, more seafood selections, and more expensive wines, raising sales by more than 10%. In a large company with large database or large systems for separate functions such as manufacturing, sales, and accounting, special capabilities and tools are required for analyzing vast quantities of data and for accessing data from multiple systems. And these capabilities include data warehousing, data mining, and tools for accessing internal databases, of course, through the use of web. In managing data resources, setting up a database is only a start. In order to make sure that the data for your business remain accurate, reliable, and readily available to those who need it, your business will need special policies and procedures for data management.
smallest unit of data a computer can handle. So a group of bits called a byte, and a byte represents a single character, which can be a letter, a number, or another symbol. So a grouping of characters into a word, a group of words, or a complete number, such as a person's name or age perhaps, is what we call a field. So a group of related fields, such as, let's say, student's name, or may it be the course taken, the date, and the grade, comprises a record. And a group of records of the same type is called a file. For example, the records in figure 6.1 could constitute a student's course file. So a group of related files makes up a database, okay? So the student course file illustrated in figure 6.1 could be grouped with files on students' personal histories and financial backgrounds to create a student's database. And a record describes an entity. And if we say an entity, it is a person, place, thing, or event on which we store and maintain information, and each characteristic or quality describing a particular entity is called an attribute. So for example, student ID, course, date, and grade are attributes of the entity course, all right? If that makes sense. And the specific values that these attributes can have are found in the fields of the record describing the entity course. Now, under problem with the traditional file environment, take note that in most organizations, systems tended to grow independently without a company-wide plan. And accounting, finance, manufacturing, human resources, and sales and marketing all developed their own systems and data files. Now, as you can see in figure 6.2, it illustrates the traditional approach to information processing. And if you can notice, each application, of course, required its own files and its own computer program to operate. For example, the human resources functional area might have a personal master file, a payroll file, a medical insurance file, a pension file, a mailing list file, and so forth, until tens, perhaps hundreds of files and programs existed. Now, in the company as a whole, this process actually led to multiple master files created, maintained, and operated by separate division or departments. Now, as this process goes on for 5 to 10 years, okay, now the organization is saddled with hundreds of programs and applications that are very difficult to maintain and manage. And that being said, the resulting problems are data redundancy and inconsistency, program data dependence, inflexibility, poor data security, and an inability to share data among applications. Now, in order for us to understand this one better, let us discuss them one by one, starting with data redundancy and inconsistency. So if we say data redundancy, it is the presence of duplicate data in multiple files or in multiple data files so that the same data are stored in more than one place or location. So meaning data redundancy occurs when different groups in an organization independently collect the same piece of data and store it independently of each other. All right, so that is what we call data redundancy. And aside from that, data redundancy wastes storage resources and also leads to data inconsistency, where the same attribute may have different values. For example, in instances of the entity course illustrated in figure 6.1, the data may be updated in some systems but not in others. So the same attribute, let's say student's ID, may also have different names in different systems throughout the organization. So some systems might use student ID and others might use ID, for example. So that problem is what we call data inconsistency. Aside from data redundancy and inconsistency, we also have what we call program data dependence. And what is meant by program data dependence? If it's a program data dependence, it refers to the coupling of data stored in files and these specific programs required to update and maintain those files such that changes in programs require changes to the data. So this means to say that every traditional computer program has actually to describe the location and nature of the data with which it works. So in a traditional file environment, for example, any change in a software program could require a change in the data accessed by that program, all right? Now, one program might be modified from a 5-digit to a 9-digit zip code, okay? So if the original data file were changed from, let's say, 5-digit to 9-digit zip codes, then other programs that required the 5-digit zip code would no longer work properly, all right? If that makes sense. So such changes could cost millions of dollars to implement properly, all right? So that is what we call program data dependence problem. And aside from this, another problem that we have is what we call lack of flexibility. Now, a traditional file system can deliver routine scheduled reports after extensive programming efforts, but it cannot deliver ad hoc reports or respond to unanticipated information requirements in a timely fashion. So this means that the information required by ad hoc request is somewhere in the system, but maybe too expensive to retrieve. Therefore, several programmers might have to work for weeks to put together the required data items in a new file, all right? So that's what we call lack of flexibility. And another problem that we may encounter that would be what we call poor security. And under poor security, because there is a little control or management of data, access to and dissemination of information may be out of control. This means that management may have no way of knowing who is accessing or even making changes to the organization's data. So this is what we call poor security. And finally, the last problem that we may encounter that would be lack of data sharing and availability. So because of pieces of information in different files and different parts of the organization cannot be related to one another, then it is virtually impossible for information to be shared or accessed in a timely manner. So what do we mean by this? This means that information cannot flow freely across different functional areas or perhaps different parts of the organization. And if this happens, if users find different values of the same piece of information in two different systems, then they may not want to use these systems because they cannot trust the accuracy of their data. All right, so this is what we call lack of data sharing and availability. All right, so the next key area that we're going to be discussing now, that would be the major capabilities of database information or database management systems or DBMS. And why is irrational DBMS so powerful? Now, take note that database technology cuts through many of the problems of traditional file organization, right? So a more rigorous definition of a database is a collection of data organized to serve many applications efficiently by centralizing the data and controlling redundant data. So as you can see on the sample image, that's an example of a database. So in this case, a database, rather than storing data in separate files, For each application, data appear to users as being stored in only one location. So a single database services multiple applications. For example, instead of a corporation storing employee data in separate information systems and separate files for personnel, payroll, and benefits, the corporation could create a single common human resources database. So what is meant by a database management systems then, or DBMS? If we say database management system, it is actually a software, all right, that permits an organization to centralize data, manage them efficiently, and provide access to the stored data by application programs. So the DBMS acts as an interface between application programs and the physical data files. So when the application program calls for a data item, such as, let's say, gross pay, okay? So the DBMS finds this item in the database and presents it to the application program. So using traditional data files, the programmer would have to specify the size and format of each data element used in the program and then tell the computer where they were located. And aside from that, a DBMS relieves the programmer or end user from the task of understanding where and how the data are actually stored by separating the logical and physical views of the data. So in this case, the logical view presents data as they would be perceived by end users or business specialists, whereas the physical view shows how data are actually organized and structured on physical storage media. Now, as you can see in figure 6.3, the databases management software makes the physical database available for different logical views required by users. For example, for the HR or human resources database illustrated in this particular figure, figure 6.3, a benefit specialist might require a view consisting of the employee's name, social security number, and health insurance coverage. So a payroll department member might need data such as the employee's name, social security number, gross pay, and net pay as well. So the data for all these views are stored in a single database where they can be more easily managed by the organization. So how a DBMS solves the problems of the traditional file environment then? Well, a DBMS reduces data redundancy and inconsistency, the one we discussed earlier, okay, by minimizing isolated files in which the same data are being repeated. So the DBMS may not enable the organization to eliminate data redundancy entirely, but it can help control redundancy. So this means that even if your organization maintains some redundant data, well, using a DBMS eliminates data inconsistency because, like I said earlier, the DBMS can help the organization ensure that every occurrence of redundant data has the same values. So the DBMS uncouples programs and data, enabling data to stand on their own. And under relational DBMS, take note that contemporary DBMS use different database models to keep track of entities, attributes, and even relationships. So the most popular type of DBMS today, if you may know, for PCs, as well as for larger computers and mainframes, is the relational DBMS. So what do we mean by relational DBMS then? If we say relational databases, they represent data as two-dimensional tables, okay, called relations. And tables may be referred to as files. So each table contains data on an entity and its attributes. For example, Microsoft Access is a relational DBMS for desktop computers, whereas DB2, Oracle Database, and Microsoft SQL Server are relational DBMS for large mainframes and mid-range computers. MySQL is a popular open source DBMS. So let's try to take a look at how a relation database organizes data about suppliers and parts. Now, as you can see in figure 6.4, it illustrates the relational database tables, right? Now, as you can notice, the database has a separate table for the entity supplier, okay? And a table for the entity part, if you can see that, okay? So the supplier is in the upper part, and the part is in the lower part. Now, as you may notice, each table consists of a grid of columns and rows of data, correct? Now, each individual element of data for each entity is actually stored as a separate field, and each field represents an attribute for that entity. Now, fields in a relation database are also called columns, okay? Take note. And for the entity supplier, the supplier identification number, name, street, city, state, and even the zip code are stored as separate fields within the supplier table, and each field represents an attribute for the entity supplier. Now, the actual information about a single supplier that resides in a table is called row. Now, what do we mean by row? If we say rows, these are commonly referred to as records, or in very technical terms as tuples. Now, the field of supplier name in the supplier table, okay, let me go back to our example or figure. So the field for supplier name in the supplier table uniquely identifies each record so that the record can be retrieved, updated, or sorted. So it is called a key field. So each table in a relation database has one field that is designated as its primary key. So what do we mean by primary key then? So if we say primary key, this key field is the unique identifier for all the information in any row of the table, and this primary key cannot be duplicated. So in order for us to better understand this, let me go back to our figure. So figure 6.4. Now, for example, in this case, supplier number, okay, is the primary key for the supplier table, and part number is the primary key for the part table. And take note that supplier number appears in both the supplier and part tables, right? If you can see. And in the supplier table, supplier number is the primary key, okay? So next, when the field supplier number appears in the part table, well, it is called a foreign key and is essentially a lookup field to look up data about the supplier of a specific part. All right. So the next key subtopic, that would be the capabilities of data management system, or DBMS. Now, as you can see, a DBMS includes capabilities and tools for organizing, managing, and accessing the data in the database. So the most important are its data definition language, data dictionary, and data manipulation language as well. Now take note that DBMS have a data definition capability to specify the structure of the component of the database. Now that being said, it would be used to create database tables and to define the characteristics of the field in each table. Now, this information about the database would be documented in the data dictionary. So a data dictionary is an automated or manual file that stores definition of data elements and their characteristics. So Microsoft Access, for example, has a rudimentary data dictionary capability that displays information about the name, the description, the size, the type, or even the format and other properties of each field in a table, as you can see in figure 6.6. Now, as you may notice, data dictionaries for large corporate databases may capture additional information such as, let's say, usage, or we also have ownership. When we say ownership, it is who in the organization is responsible for maintaining the data. And aside from usage and ownership, we include authorization, security, and the individuals, business functions, programs, and reports that use each data element. And under querying and reporting, take note that DBMS includes tools for accessing and manipulating in databases. So most DMS have a specialized language called a data manipulation language that is used to add, change, delete, and retrieve the data in the database. So this language that I'm referring to actually contains commands that permit end users and programming specialists to extract data from the database to satisfy information requests and develop applications as well. So the most prominent data manipulation language today is what we call as structured query language, or the SQL. Now, as you can see in figure 6.7, it illustrates the SQL query that would produce the no resultant table in figure 6.5. Now, as you can notice, users of DBMS for large and mid-range computers, such as DB2, Oracle, or SQL Server, would employ SQL to retrieve information they needed from the database. So Microsoft Access also uses SQL, okay? However, it provides its own set of user-friendly tools for querying databases and most especially for organizing data from databases into more polished reports. Now, in Microsoft Access, if you can notice, you will find features that enable users to create queries by identifying the tables and fields they want and the results, and then selecting the rows from the database that meet particular criteria. So these actions in turn are translated into SQL commands. Okay, now as you can see in figure 6.8, it illustrates how the same query as the SQL query to select parts and suppliers would be constructed using the Microsoft Access query building tools. Now, Microsoft Access and other DBMS include capabilities for report generation. And why is that so? So that the data of interest can be displayed in a more structured and polished format, okay, than would be possible just be querying. So in other words, Crystal Reports is a popular report generated for large corporate DBMS, okay, although it can also be used with Access. So Access also has capabilities for developing desktop system applications. So these include tools for creating data entry screens, reports, and developing the logic for processing transaction. So under designing databases, to create a database, one must first, you need to understand the relationships among your data. Second, the type of data that will be maintained in your database system. Third, how the data will be used. And finally, how the organization will need to change to manage data from a company-wide perspective. So the database requires both. First, we have a conceptual design, and second, we have a physical design. So the conceptual or logical design of a database is an abstract model of the database, okay, from a business perspective, whereas the physical design shows how the database is actually arranged or direct access storage devices. So in order for us to better understand more, let us discuss normalization and entity relationship diagrams. So like I said earlier, if we say conceptual database design, it actually describes how the data elements in the database are to be grouped. So the design process identifies relationships among data elements and the most efficient way of grouping data elements together to meet business information requirements. This means to say that the process also identifies redundant data elements, okay, and the groupings of data elements required for specific application programs. So therefore, groups of data are being organized, refined, and streamlined until an overall logical view of the relationships among all data in the database emerges. So to use a relation or relational database model effectively, then complex groupings of data must be streamlined to minimize redundant data elements and awkward many-to-many relationships. So if we say normalization, it is the process of creating small, stable, yet flexible and adaptive data structure from complex groups of data. Now, figure 6.9 and 6.10 illustrate this process, okay? Now, as you can see in figure 6.9, it illustrates a normalized relation to order, correct? Now, as you can see, a normalized relation contains repeating groups. For example, there can be many parts and suppliers for each order. So there is only a one-to-one correspondence between order number and order date. On the other hand, as you can see in figure 6.10, it illustrates normalized tables created from orders, right? And after normalization, the original relation order has been broken down into 4 smaller relations. So the relation order is left with only 2 attributes, and the relation line item has a combined or concatenated key consisting of order number and part number. So in the particular business modeled here, an order can have more than one part, okay? But each part, take note, is provided by only one supplier. So this being said, if we build a relation called order with all the fields included here, we would have to repeat the name and address of the supplier for every part on the order, even though the order is for parts from a single supplier. So this relationship contains what are called repeating data groups. Why? Because there can be many parts on a single order to a given supplier, okay? So a more efficient way to arrange the data is to break down order into smaller relations. So in this case, each of which describes a single entity. So if we go step by step and normalize the relation order, then we emerge with the relations illustrated in 6.10. Now, relational database systems try to enforce referential integrity rules to ensure that relationships between coupled tables remain consistent. In other words, when one table has a foreign key that points to another table, okay, so you may not add a record to the table with a foreign key unless there is a corresponding record in the linked table. So in the database we examined earlier in this chapter, the foreign key supplier number links the part table to the supplier table, right? If we can recall. So we may not add a new record to the part table for a part with supplier number 8266 unless there is a corresponding record in the supplier table for supplier number 8266. So that being said, we must also delete the corresponding record in the part table if we delete the record in the supplier table for supplier number 8266. So in other words, we should not have parts from non-existent suppliers, okay? Now, database designers document their data with an entity relationship diagram. Now, as you can see in figure 6.11, it illustrates an entity relationship diagram. Now, if you can notice, this diagram illustrates the relationship between the entities supplier, part, line item, and order, okay? Now, the boxes represent entities, okay? Now, the lines connecting the boxes represent relationships. So, a line connecting two entities that ends in two short marks designates a one-tune relationship, and a line connecting two entities that ends with a crow's foot topped by a short mark indicates a one-to-many relationship. Okay, take note. Now, this figure also shows that one order can contain many line items. So a part can be ordered many items and appear many times as a line item in a single order. So therefore, each part can have only one supplier, but many parts can be provided by same supplier. It can't be emphasized enough. If the business doesn't get its data model right, the system won't be able to serve the business well. The company system will not be as effective as they could be because they'll have to work with data that may be inaccurate, incomplete, or difficult to retrieve. So understanding the organization's data and how they should be represented in a database is perhaps the most important lesson you can learn from this course. Now, in order for us to better understand this better, let me give you an example. So, for example, famous footwear, a shoe store chain with more than 800 locations in 49 states, could not achieve its goal of having the right style of shoe in the right store for sale at the right price because its database was not properly designed for rapidly adjusting store inventory. Now, in this case, the company had an Oracle relational database running on a mid-range computer, but the database was designed primarily for producing standard reports for management rather than for reacting to marketplace changes. Now, management could not obtain precise data on specific items in inventory in each of its stores. And therefore, the company had to work around this problem by building a new database where the sales and inventory data could be better organized for analysis and inventory management. All right, so that ends our discussion for the second key area. And finally, the last key area that we're going to be discussing is going to be the different principal tools and technologies for accessing information from databases to improve business performance and decision making. Now, as you may know, businesses use their databases to keep track of basic transactions such as, let's say, paying suppliers or processing orders, keeping track of your customers, and even paying your employees. But we also need databases to provide information that will help the company run the business more efficiently and help managers and employees make better decisions. So if a company wants to know which product is the most popular or who is its most profitable customer, then the answer lies in the data. So the challenge of big data, most of data collected by organizations used to be transaction data, right? That could easily fit into rows and columns of relational database management systems. So we are now witnessing an explosion of data from web traffic, email messages, and social media content such as tweets or even status messages, as well as machine-generated data from sensors used in smart meters, manufacturing sensors, and electrical meters, so, or from electronic trading systems. Now, this data may be unstructured or semi-structured and thus not suitable for relation database products that organize data in the form of columns and rows. So we now use the term big data to describe these data sets with volumes so huge that they are beyond the ability of typical DBMS to capture, store, and analyze. So what is meant by big data then? If I say big data, it doesn't refer to any specific quantity, but usually refers to data in the petabyte and exabyte range. In other words, billions to trillions of records, all from different sources. So aside from that, big data are produced in much larger quantities and much more rapidly than traditional data. For example, a single jet engine is capable of generating 10 terabytes of data in just 30 minutes, and there are more than 25,000 airline flights each day. Now, even though tweets are limited to 140 characters each, Twitter generates more than 8 terabytes of data daily, okay? Now, according to the International Data Center, or IDC, data are more than doubling every 2 years, so the amount of data available to organization is skyrocketing. Now, under business intelligence infrastructure, suppose you wanted concise, reliable information about current operations, trends, and even changes across the entire company. So, supposing if you worked in a large company, the data you need might have to be pieced together from separate systems, okay, such as sales, manufacturing, and accounting, and even from external sources such as demographic or competitor data. So increasingly, you might need to use big data. So a contemporary infrastructure for business intelligence has an array of tools for obtaining useful information from all the different types of data used by business today, including semi-structured and unstructured big data in vast quantities. And these capabilities include data warehouse and data marts, Hadoop, in-memory computing, and analytical problems. So some of these capabilities are available as cloud services. Now, in order for us to better understand each of these capabilities, let us discuss them one by one, starting with data warehouse and data marts. Now, if I say data warehouse, it is a database that stores current and historical data of potential interest to decision makers throughout the company. Now, this means that the data originate in many core operational transaction systems such as systems of sales, customer accounts, and manufacturing, and may include data from website transaction. And aside from that, data warehouse extracts current and historical data from multiple operational systems inside the organization. Now, this means that these data are combined with data from external sources and transformed by correcting inaccurate and incomplete data and restructuring the data for management reporting and analysis before being loaded into the data warehouse. So on the other hand, companies often build enterprise-wide data warehouses where a central data warehouse serves the entire organization, or they create smaller, decentralized warehouses called data marts. So if we say data mart, it is a subset of a data warehouse in which is summarized or highly focused portion of the organization's data is placed in a separate database for a specific population of users. For example, a company might develop marketing and sales data marts to deal with customer information. Okay, so that's what we call data mart. And on the other hand, for Hadoop, take note that relational DBMS and data warehouse products are not well suited for organizing and analyzing big data or data that do not easily fit into columns and rows used in their data models, right? Now, that being said, for handling unstructured and semi-structured data in vast quantities, as well as structured data, organizations are using Hadoop. If I say Hadoop, it is an open source software framework managed by the Apache Software Foundation that enables distributed parallel processing of huge amounts of data across inexpensive computers. So in other words, it breaks a big data problem down into sub-problems, okay? And it distributes them among up to thousands of inexpensive computer processing nodes, and then combines the result into a smaller data set that is easier to analyze. So you've probably used Hadoop to find the best airfare on the internet, get directions to a restaurant, do a search on Google, or even connect with a friend on Facebook. Okay, so aside from Hadoop, we also have in-memory computing. So another way of facilitating big data analysis is the use of in-memory computing. And if we say in-memory computing, it relies primarily on a computer's main memory or RAM for data storage. So here, users access data stored in system, primarily memory. So thereby eliminating bottlenecks from retrieving and reading data in a traditional disk-based database and dramatically shortening query response times. Now, in-memory processing makes it possible for a very large sets of data amounting to the size of a data mart or even small data warehouse to reside entirely in memory. So because of that, complex business calculations that used to take hours or days are able to be completed within seconds, and this can even be accomplished using handheld devices. And finally, aside from in-memory computing, we also have analytic platforms. Now, commercial database vendors have developed specialized high-speed analytic platforms using both relational and non-relational technology that are optimized
Okay, so again, to summarize our discussions, no? So number one question a while ago is, what are the problem of managing data resources in a traditional file environment, and how are they solved by a database management system? Again, traditional file management technique made it difficult for organization to keep track of all the pieces of data they use in a systematic way and to organize this data so they can be easily accessed. Different functional areas and groups were allowed to develop their own files independently. So over time, this traditional file management environment creates problems such as data redundancy and inconsistency, program data independence, and flexibility, poor security, and lack of data sharing and availability. A database management system solves these problems with software that permits centralization of data and data management so that businesses have a single consistent source for all their data needs. Using a DBMS minimizes redundant and inconsistent files. For question number 2, what are the major capabilities of DBMS and why is a relational DBMS so powerful? The principal capabilities of DBMS includes a data definition capability, a data dictionary capability, and a data manipulation language. The data definition capability specifies the structure and content of the database. And the data dictionary is an automated or manual file that stores information about the data in the database, including names, definitions, formats, and descriptions of data elements. The data manipulation language, such as SQL or structured query language, is a specialized language for accessing and manipulating the data in the database. The relational database is the primary method for organizing and maintaining data today in information system because it's so flexible and accessible. It organizes data in two-dimensional tables called relations with rows and columns. Each table contains data about an entity and its attribute. Each row represents a record and each column represents an attribute or field. And each table also contains key field to uniquely identify each record for retrieval or manipulations. So relational database tables can be combined easily to deliver data required by users, provided that any two tables share a common data element. Question number 3, of course, is what are some important database design principles? Designing a database requires both a logical design and a physical design. The local design models the database from a business perspective. The organization's data model should reflect its key business processes and decision-making requirements. The process of creating small, stable, flexible, and adaptive data structures from complex groups of data when designing a relational database is term normalization. A well-designed relational database will not have many-to-many relationships, and all attributes for a specific entity will only apply to that entity. It will try to enforce referential integrity rules to ensure that relationship between coupled tables remain consistent. And an entity relationship diagram graphically depicts the relationship between entities or the tables in a relational database. For question number 4, what are the principal tools and technologies for accessing information from databases to improve business performance and decision-making? Powerful tools are available to analyze and access the information in databases. A data warehouse consolidates current and historical data from many different operational systems in a central database designed for reporting and analysis. Data warehouse support multidimensional data analysis, also known as online analytical processing or OLAP. OLAP represent relationship among data as a multidimensional structure, which can be visualized as cubes of data and cubes within cubes of data, enabling more sophisticated data analysis. Data mining analysis large pools of data, including the contents of data warehouses, to find patterns and rules that can be used to predict future behavior and guide decision-making. Text mining tools help businesses analyze large unstructured data sets consisting of text. Web mining tools focus on analysis of useful patterns and information from the World Wide Web, examining the structure of website and activities of website users, as well as the contents of web pages. Conventional databases can be linked via middleware to the web or a web interface to facilitate user access to an organization's internal data. For question number 5, what are information policy, data administration, and data quality assurance essential for managing the firm data resources? Of course, developing database environment requires policies and procedure for managing organizational data, as well as good data model and database technology. So a formal information policy governs the maintenance, distribution, and use of information in the organizations. In large corporation, a formal data administration functions is responsible for information policy, as well as for data planning, data dictionary development, and monitoring data usage in the firm. Data that are inaccurate, incomplete, or inconsistent create serious operational and financial problems for businesses because they may create inaccuracies in product pricing, customer accounts, and inventory data, and lead to inaccurate decisions about the actions that should be taken by the firm. Firms must take special steps to make sure they have a high level of data quality. These include using enterprise-wide data standards, databases designed to minimize inconsistent and redundant data, data quality audits, and data cleansing software. And I think that's it. And this will be our reference. Okay? Laudon Kenneth C. and Laudon Jane P. 2018 Management Information System Managing the Digital Firm 15th edition by Person Education Limited. So that's it. And thank you for attending our class. And good day, everyone.